Hi, I'm Prof and welcome to Chemistry Matters, and today we are going to be talking about the solubility product. Okay, so one of maybe the first experiments that your chemistry teacher might have made you do is to take a solution of sodium chloride, a clear colourless solution, and add a couple of drops of a clear colourless solution of silver nitrate to that. And then magically, you get this beautiful white precipitate coming out in the test tube. And that white precipitate is silver chloride. Okay? And your teacher at that point may have told you that silver chloride is insoluble. In which case, your teacher would be horribly wrong. Okay? So let's talk about that now. Okay? And we're going to use silver chloride as our example, okay? Solid silver chloride. Now, as I say, it does form a precipitate when you add silver ions to chloride ions, but only under certain conditions, in fact. So what happens if we take solid silver chloride, lovely white precipitate, or white solid, and put it into water? Well, if we do that, then to our eye, nothing really is obviously happening, but in fact it is. And what is happening is that a very small amount of your solid silver chloride is in fact dissolving. And it dissolves to give silver ions, aqueous silver ions, and aqueous chloride ions. And that's what will happen when you take your solid silver chloride, put it in water. Now, this is an equilibrium process, which means the reaction's going the other way as well, that silver ions and chloride ions are getting together and forming solid silver chloride. So even though it appears to us that nothing's happened, something has. The reason that it appears to us nothing happened is because the amount of this that gets formed is indeed very small. Okay, so let's quantify that. Let's say, right, how much of these silver and chloride ions are formed when we put solid silver chloride in water? Well, because it's an equilibrium process, we can write an equilibrium constant for it. And because it's a special equilibrium, we give it a special name, KSP, otherwise known as the solubility product. Okay? Now, what have we got here? Let's write the equilibrium constant for this process. We've got an aqueous ion here, an aqueous ion here, so they're going to go in. We've got a solid here. We know pure solids don't appear in equilibrium constant expressions, and so that's not going to go in. And so our equilibrium constant expression is quite simply merely the concentration of silver ion multiplied by the concentration of chloride ion. Okay? And the actual value of KSP for this is 1.8 times 10 to the power of minus 10. Okay. Now, excuse me, you can see straight away from the magnitude of this number that this equilibrium is going to lie very, very, very much to the left-hand side, isn't it? Okay? A tiny number, way, 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 way less than 1. Obviously, the products are going to predominate at equilibrium, which means that the amount of this in your solution, in your aqueous solution, is going to be very, very small. Okay, now let's then figure out just how small. Let's figure out the concentration of silver ion and chloride ion, the actual concentration, by using the value of KSP here. So how do we do this? Well, we're going to say, right, let's look at the stoichiometry, as we always do, the stoichiometry of this equilibrium here. 1 mole of silver chloride will give 1 mole of Ag plus and 1 mole of chloride ion. Okay, so in other words, stoichiometrically, it's a 1-to-1 type of process here. Okay, so let's say that S moles of this dissolve. Okay, so when we put our silver chloride in water, S moles of it are going to dissolve. So therefore, if S moles of this dissolve, then we are going to get, we'll put it below it, S moles of that, and we're going to get S moles of that in solution, aren't we? Okay? So therefore, we are going to say that the concentration of this is going to be S moles per litre. The concentration of that is going to be S mole per litre. Okay, so if S moles of this, just to reiterate, if S moles of this dissolves in 1 litre of water, then the concentration of Ag plus is going to be S, and the concentration of Cl minus is going to be S. So therefore, we can rewrite our KSP expression. We can say that KSP then is going to be S, which is the concentration of Ag plus, multiplied by S, which is the concentration of Cl minus, which is equal to S squared, which equals 1.8 times 10 to the power of minus 10. Okay, so therefore, S is going to be equal to the square root of 1.8 times 10 to the minus 10, and that then becomes 1.34 times 10 to the power of minus 5 mole per litre. Okay, and you can see that this is a very small number, 10 to the minus 5 mole per litre. So we're quite right in saying that when we suspend silver chloride in aqueous solution, to our eyes it really does look like nothing's happening. Something is, but it's only happening to a very, very small extent. Okay, so essentially what we have done here is we've related the value of KSP, the solubility product, to the solubility of the salt in moles per litre. Okay, so remember this S, that refers to the solubility of silver chloride in water, okay, S moles per litre. And we have said for this particular example that KSP is equal to the solubility squared. Now, that is only true for this particular type of reaction. In other words, a 1-to-1 type of dissociation. In other words, 1 mole of this gives you 1 mole of that and 1 mole of that. And if that's true, then KSP is equal to S squared. Now, what about for other types of sparingly soluble materials, okay? And when I say sparingly soluble, remember I said that the teacher may have told you that silver chloride's insoluble. It's not insoluble. It's got a solubility of 1.34 times 10 to the minus 5 mole per litre, okay? So we shouldn't say that silver chloride is insoluble. Insoluble means that it doesn't dissolve at all. It does, but only to a tiny extent. So therefore, it is best to say that silver chloride is slightly soluble or sparingly soluble, okay? Now, so for a sparingly soluble salt AB, as we've just shown, for silver chloride, KSP is equal to S squared, okay? For a sparingly soluble salt AB2, okay, then KSP is equal to 4S cubed. And that might ring some bells with some of you. How do we get that? Well, let's write your balanced chemical equation in this case. Now let's use a real example. Let's use good old lead iodide, lovely yellow insoluble, sparingly soluble salt, and that gives Pb2 plus 2I minus, both of them aqueous. Then if we were to write the KSP expression for this, KSP is equal to lead concentration multiplied by the iodide concentration squared. That's the important thing. Now, let's use the same reasoning as we did for the silver chloride example and say, right, if S moles of lead iodide dissolve in 1 litre, then the concentration of lead at equilibrium is going to be S moles per litre. The concentration of iodide at equilibrium, now for every mole of lead iodide that dissolves, we get 2 moles of iodide. So if S moles of this dissolves in a litre, we're going to end up with 2 S moles of that in a litre, okay? The concentration is going to be 2 S moles per litre. So now we take these numbers and substitute them in our KSP equation. Okay, so KSP, therefore, is equal to lead concentration, which we're saying is S, excuse me, multiplied by iodide concentration. The iodide concentration is 2S all squared. Okay? Now, what is 2S all squared? It's not just 2S squared, it's 4S squared. It's 2S times 2S, okay? Which is 4S squared multiplied by S, and that gives you 4S cubed. So KSP for an electrolyte like this, a 1 to 2 electrolyte we call it, KSP is going to be equal to 4S cubed, okay? We can use, sorry, I've got the hem bug today. For a 3 to 1 electrolyte, we can use exactly the same reasoning if we've got AB3, and KSP for that is in fact 27S to the 4. I'm not going to show you how to do that. I'm going to leave that as an exercise for you, and if you're feeling extremely brave, then if we have a situation like this with A to B3, then KSP is equal to 108S to the power of 5. And if you can do that one, you can do any of these. What's the use of this? The use of this is basically relating the value of KSP to the solubility, to the molar solubility of your sparingly soluble material. Okay? KSP and S. The two important things in all of this, okay? So those are your relationships between KSP and S for the only really common types of electrolytes. Your 1 to 1, your 1 to 2, your 1 to 3, and your 2 to 3. You can hopefully derive all of those now with what you've learned in this video. And that's all I've got to tell you today, and we'll see you